Hello friends, welcome to my lecture on classification and canonical forms of second order partial differential equations. There will be two lectures on this topic. This is first of the two lectures. Let us consider a partial differential equation of the type RR plus SS plus TT plus Fx by Z PQ equal to 0. As you know, P is partial derivative of Z with respect to x, Q is partial derivative of Z with respect to y, R is second order partial derivative of Z with respect to x, and S is second order partial derivative of Z with respect to x and y, and T is second order partial derivative of Z with respect to y. Now, this equation can be written as Lz plus Fx by Z Pq equal to 0, where L is the differential operator given by R del square over del x square plus S del square over del x del y plus T del square over del y square. So, Lz will be equal to, if we assume L to be this differential operator, then Lz is R zxx plus S zxy plus T zyy, and by our notation zxx is small r, zxy is small s, and zyy is small t. So, we get RR plus SS plus TT, this is Lz, and so we can write this Lz plus Fx by Z Pq equal to 0. Now, here these R, S, T are continuous functions of x and y possessing continuous partial derivatives of as high an order as may be necessary. By a suitable change of the independent variables x and y, we shall show that the equation 2 Lz plus Fx by Z Pq equal to 0 can be reduced to one of the three canonical forms which are easily integrable. Now, let us suppose that the independent variables x and y are changed to the independent variables u and b by the equations u equal to uxy and v equal to vxy. Then since p is equal to partial derivative of z with respect to x, by chain rule of differentiation we can write partial derivative of z with respect to u as partial derivative of z with respect to x as partial derivative of z with respect to u into ux plus partial derivative of z with respect to v into vx. Similarly, partial derivative of z with respect to y can be written as partial derivative of z with respect to u into uy plus partial derivative of z with respect to v into by. So, we have p and q by using the chain rule. Now, when we go to the second order partial derivatives, that is we find r, s and t. Okay, we find r, s and t. R will be equal to second order partial derivative of z with respect to x, s will be delta square z over delta x delta y, and t will be delta square z over delta y square. So, when we find the second order partial derivatives of z with respect to x and y, we arrive at these expressions. R is equal to this expression, s is equal to this expression, and t is equal to this expression. I will show you how we arrive at the equation for r. Similarly, you can derive the equations for s and t. The values of how we get the value of r, let us in the next slide I will show you how we get this. So, we have p equal to zx, which is equal to zu into ux plus zb into vx. Now, zxx r is equal to partial derivative of p with respect to x, which is zxx. This is equal to partial derivative of the right hand side with respect to x. Now, let us apply this differential operator on the two terms inside. So, we have now zu and ux are functions of x and y. So, I can write using the formula for the derivative of a product of two functions. We have a partial derivative of z with z u with respect to x into u x plus z u into partial derivative of u x with respect to x will be u x x, and similarly here partial derivative of z b with respect to x into b x plus z b into partial derivative of b x with respect to x. So, we will have b x x. Now, in order to now our problem is to find the partial derivative of z u with respect to x. Z is a function of x n by are functions of u and b. So, z is a function of u and b. Okay. So, z u is again when we differentiate z with respect to u, z u is again a function of u and b. So, its partial derivative with respect to x can be found from the partial derivative of this one, from this equation. Here this is what? This is, let me write like this. Okay. This equation is valid for any function z of u and b. So, it will also be valid for z u. So, I can write from this equation replacing z by z u. And what I get is z u u into u x plus z u b into b x. Similarly, similarly we can find the partial derivative of z b with respect to u with respect to x. Okay. Similarly, now this z b is also a function of u and b. So, I can replace here z by z b. So, delta over delta x z b equal to delta over delta u of z b into delta u by delta x plus delta over delta b of z b into delta b by delta x. And this is what? This is z u b into u x, and we have z b v into v x. So, let us put these values here. So, first we put this value. So, this is equal to z u u into u x plus z u b into v x multiplied by u x plus z u into u x x plus, now we put the value of this partial derivative of z b with respect to x. So, z u b into u x plus z b b into b x multiplied by b x plus z b into b x x, and then you can write it as z u u into u x whole square multiplying by u x and z u b into u x into b x plus z u into u x x plus z u b into u x b x plus z b b into b x whole square and then z b into b x x, and this term and this term are same. So, I can write z u u into u x square plus 2 times z u b into u x into b x plus z u into u x x plus z b b into b x whole square plus z b into b x x. Now, let us see if this is the value of r. So, r is z u u into u x whole square, we have z u u into u x whole square, then we have 2 z u b u x b x which we have here, and then we have z b b into b x whole square. So, we have z b b into b x whole square, and then we have z u into u x x. So, we have z u into u x x, and then we have z b into b x x. So, we get z b into b x x. So, this is how we get r. You can similarly find the other two second order partial derivatives s and t. The procedure is the same. Now, let us put these values of p q r s t. We have found the values of p q r s and t. Let us put these values in the equation 1, in this equation. In this equation, let us put the values of r s t p q, okay. And then simplifying, we get, you can simplify the that equation, you will arrive at a times z u u plus 2 b times z u b plus c times z b b plus a function of u b z z u z b equal to 0. So, we have changed from the independent variables x and y to the independent variables u and b, and the equation 1 now gives us this equation 3. Here the values of a, b, c are: a is r times u x square plus s times u x u y plus t times u y square, and b is r times u x b x plus half of s times u x b y plus u y b x plus t times u y b y. C is equal to r times b x square plus s times b x b y plus t times b y whole square, and f u b z z u z b is the transformed form of this f x y z p q equal to 0. So, this is the transformed form of that. Now, now we shall determine the functions u and b, okay. We have changed from the independent variables x and y to the new variables u and b. We will determine u and b so that the equation 3, this equation 3 reduces to the simplest possible form. Why we do this? We are doing this to make the equation integrable. So, the procedure becomes simple when the discriminant s square minus 4 r t of the quadratic form 4, okay. This is the quadratic form r u x square plus s u x u y plus t u y square, okay. So, this quadratic form is everywhere either positive, or negative, or 0. Let us discuss these three cases separately. First, we discuss the case when r square s square minus 4 r t of the quadratic form 4 is positive. So, let us consider the case when s square minus 4 r t is greater than 0, then the equation this one r lambda square plus s lambda plus t. So, we have this, then the roots of the lambda 1 lambda 2 of the equation r lambda square plus s lambda plus t equal to 0 are real and distinct, because if you find this is a second order equation in lambda, if you find the roots of this, then if the discriminant s square minus 4 r t is greater than 0, the roots of this equation will be real and distinct, and the coefficients of del square z over del u square and del square z over del b square in the equation 3 will vanish. Let us see here the coefficient of this second order derivative in u and the second order derivative in b, that is a and c, will vanish if we choose our u and b in such a way that delta u by delta x equal to lambda 1 delta u by delta y delta v over delta x equal to lambda 2 into delta v over delta y, where lambda 1 and lambda 2 are functions of x and y, because r, s, t depend on x and y. Now, since lambda 1 is a root of this equation, r lambda square plus s lambda plus t equal to 0, it will satisfy this equation. So, we will have r lambda 1 square plus s lambda 1 plus t equal to 0. Now, what we do is, let us use equation number 6, this u x equal to lambda 1 u y. So, if you use this, what we get here, r is a is equal to, you see, we are using u x equal to lambda 1 times u y. Okay. So, what is r? R, this will give you a equal to r times u x square. U x square means lambda 1 square u y square plus s times u x. U x is lambda 1 into u y plus t times u y square. So, what we can do? We can write r a is equal to r lambda 1 square plus s lambda 1 plus t times u y square. Okay. Since lambda 1 satisfies the equation r lambda square plus s lambda plus t, r lambda 1 square plus s lambda 1 plus t equal to 0. So, we get a equal to 0. Okay. Similarly, if you use this equation b x equal to lambda 2 b y, then c will be equal to b x equal to, we are using b x equal to lambda 2 b y. So, we will have c equal to r times lambda 2 square b y square plus s times b x is lambda 2 b y into b y plus t times b y square. So, we can write it as r lambda 2 square plus s lambda 2 plus t into b y square, and lambda 2 is a root of r lambda square plus s lambda plus t equal to 0. So, since lambda 2 is a root of this, we have r lambda 2 square plus s lambda 2 plus t equal to 0. So, this will be equal to 0. So, by using the relations u x equal to lambda 1 u y, v x equal to lambda 2 b y, we notice that in the equation this a and c become 0. So, we get 2b into z u b plus this equal to 0, and now what we do is, so we get this a equal to 0. Again, since lambda 2 is a root of 5, r lambda square plus s lambda plus t equal to 0, we get r lambda 2 square plus s lambda 2 plus t equal to 0. So, we get c equal to 0, and now what we do is, let us write the equation 6 in this manner. This equation u x equal to lambda 1 u y, we will write it in this form, u x minus lambda 1 u y equal to 0. Now, it is a Lagrange equation. This is of the form p p plus q q equal to r. It is of this form. Okay. So, what we have here? Here the dependent variable is u, independent variables are x and y. So, this small p and small q here are this u x and u y. Capital P is 1, capital Q is minus lambda 1, and r is equal to 0. So, we can write the characteristic equations for this Lagrange equation. We will have dx over 1 equal to dy over minus lambda 1 equal to dz upon 0. Okay. So, this is how we arrive at the Lagrange auxiliary equations. Now, let us take from this characteristic equations or auxiliary equations, we notice that du equal to 0. So, we get u equal to some constant, let us say C1, and dx by 1 equal to dy by minus lambda 1. This gives you dy plus lambda 1 dx equal to 0. dy plus lambda 1 dx equal to 0. Okay, r we can say dy by dx plus lambda 1 xy equal to 0. Okay, lambda 1 is a function of x and y. So, this will give us a solution of the form, say phi xy equal to C2. Okay. This will give you a solution of the form phi xy equal to C2, and now u is equal to C1 is a one solution of this. Okay. So, there two solutions are there, u equal to C1, phi xy equal to C2. Okay. And therefore, the general solution of these equation ux minus lambda 1 uy equal to 0, the general solution of uy equal to 0 will be a function of you can say C2 will be a function of C1 or C1 will be a function of C2. So, C2 will be a function of C1. Okay. So, we can say it is a function of let us say psi of C1. Okay. So, we can say that C2 is phi xy. Okay. So, phi xy equal to psi of u, or we can say u is a function of x and y. Okay. So, the general solution of this equation, this is a function of x and y. So, psi u can be so psi u is equal to a function of x and y. So, we can say that u is a function of x and y, and therefore, u is equal to a function of x y is the general solution of this equation ux minus lambda 1 uy equal to 0. And similarly, when we find the general solution of bx minus lambda 2 by equal to 0, the Lagrange this is Lagrange equation, the auxiliary equations are dx over 1 equal to dy over minus lambda 2 equal to dv over 0. So, this will give you b equal to constant, we will have dx over 1 equal to dy over minus lambda 2 will imply that dy over dx plus lambda 2 xy equal to 0. So, this will give you a solution of this general solution of this equation will then be of the form, say some function of xy equal to a constant. Let me say this is constant, say C1, this is constants of C2. Then we can say that since C1 and C2 are functions of each other, okay, b is a function of x and y. So, we can take b to be equal to f2 xy. Okay. C1 is a function of C2. So, we can say that b is function of x and y, and x f1 and f2 are arbitrary functions here. Now, let us see this AC minus b square. We have the expressions of a, okay, b and c. So, from the expressions of a, b and c, when you find this expression AC minus b square, you can easily prove that AC minus b square is 1 over 4 times 4 RT minus s square into ux by minus uy bx whole square. And since a and c are zeros, okay, a and c are zeros, we will have minus b square equal to 1 over 4 RT minus s square, this term will become 0. So, minus b square will be equal to this, and we can multiply by minus 1. So, b square equal to 1 by 4 s square minus 4 RT into ux by minus uy bx whole square. Now, this quantity is non-negative, okay. So, and s square minus 4 RT, s square is greater than 4 RT. So, this is also this is positive, okay. So, positive into this non-negative quantity makes it this one. Since s square minus 4 RT is greater than 0, we have b square greater than 0, okay. B square, okay, ux into by minus uy bx. U and b are functions of f x and y, they are arbitrary functions. S square is greater than 4 RT, okay. So, we can assume that this is strictly positive. So, b square is strictly positive, okay, and that means b is not equal to 0. So, when b is not equal to 0, we can divide the equation 3 by b, this equation a and c are zeros, 2b into delta square z over delta u delta b plus a function of u b z, z u z b equal to 0 will then be divided by 2b, we can divide by 2b and arrive at this equation. Z u b equal to phi some function of phi of u b z z u z b, which is the canonical form of the equation 1 in this case, and it can be then easily integrated. Now, let us look at a problem on this, say r minus x square t equal to 0. So, what we do here is that if you compare it with the standard form r r plus s s plus t t plus f x by z p q equal to 0, then we notice that r is equal to 1, s is equal to 0 and t is equal to minus x square, hence s square minus 4 r t, s square minus 4 r t is s is 0, 4 into 1. So, 0 minus 4 into 1 into minus x square. So, we get 4 x square, which is positive. So, s square minus 4 r t is greater than 0. Therefore, the equation, let us go to this equation, r lambda square plus s lambda plus t equal to 0. This equation will have two real and distinct roots. So, let us write the roots for this equation, r lambda square plus s lambda plus t equal to 0. So, let us write r lambda square plus s lambda plus t equal to 0. Let us find the roots of this. R is equal to 1. So, we have lambda square and then s is equal to 0, t is equal to minus x square. So, lambda square minus x square equal to 0, which gives lambda equal to plus minus x. So, we get the two roots, lambda 1 x y equal to x and lambda 2 x y equal to minus x. We get two real and distinct roots. Now, let us consider the two equations. We connect we write these two equations, this one u x equal to lambda 1 u y, v x equal to lambda 2 v y. We choose these equations. So, u x, now we choose u and b such that u x equal to lambda 1 times u y and b x equal to lambda 2 v y. So, what do we get? This is equal to lambda 1 is x. So, x times u y, okay, and similarly b x equal to minus. Okay. Now, let us solve this equation for the value of u. So, this is minus x, this is a Lagrange equation. So, in the case of Lagrange equation, here we have instead of z we have u. Okay. So, we have dx by 1 equal to dy y minus x equal to du upon 0, which implies that du equal to 0 and dy plus x dx equal to 0. Okay. So, du equal to 0 gives us u equal to some constant, say C1, and dy plus x dx is equal to 0 gives us y plus x square by 2 equal to C2. Now, C2 is a function of C1 or C1 is a function of C2. So, we can write C1 equal to a function of C2, that is C1 is u. Okay. So, u is equal to phi of y plus x square by 2, where phi is an arbitrary function. Let us choose u to be equal to y plus x square by 2. And similarly, the other equation, this gives you the Lagrange auxiliary equations as dx by 1 dy over x equal to dub over 0. So, this gives you dv equal to 0 and dy minus x dx equal to 0, and dv equal to 0 gives you b equal to some constant, let us say C3, and dy minus x dx equal to 0 gives you y minus x square by 2 equal to some constant, say C4. Okay. So, C3 is a function of C4. So, you can say that b is equal to some function, say psi of y minus x square by 2. Let us choose b to be y minus x square by 2. Okay. So, we find the value of u and the value of b. With this choice of u and b, a and c will be zeros, and we will get the equation of this form. Okay. So, let us see how we arrive at this canonical form. So, let us go to the this equation, r minus x square t equal to 0. Let us change r and t and x here, which are r is a partial derivative of z with respect to x, second order derivative, x t is a second order derivative of z with respect to y. So, let us change them to the corresponding derivatives with respect to the independent variables u and b. So, we consider r minus x square t equal to 0. Okay. First we find, in order to find r, let us find first p. P is equal to partial derivative of z with respect to x. So, this is zu into ux, zb into bx. Now, what is our choice? Our choice of u is y plus x square by 2. So, u is y plus x square by 2 and b is y minus x square by 2. So, this gives you ux equal to x and this gives you bx equal to minus x. So, this is zu into x and zb into minus x. Okay. So, let us now find r. R is partial derivative of p with respect to x. So, partial derivative with respect to x of zu into ux minus partial derivative of zb into x with respect to x. Okay. So, what do we have? Partial derivative with respect to x of zu into ux, ux is x here, this is x. Okay. So, derivative, so this is x and then plus zu into derivative of x with respect to x. So, 1 and then minus derivative of zb with respect to x into x plus derivative of x with respect to x. So, that is 1. So, what we get? Now, in place of z here, let us put zu, because this relation is valid for any function z of u and b. So, it is also valid for zu, because zu is a function of u and b. So, delta over delta x of zu will be equal to now delta over delta x of zu is equal to, let us put z in place of zu. So, zuu into x minus zu, when you put in place of z here, this is partial derivative of z with respect to v. So, we get zub into x. So, this is how we get the partial derivative of zu with respect to x. Similarly, partial derivative of zb with respect to x, we can get delta over delta x of zb with respect to x. So, this is this term we can find. okay, let me write only this partial derivative of ZB with respect to x. So, this we in place of Z we put ZB here and we get ZUB into x minus ZBB into x. Okay. Now, let us put these value, this value and this value here. Okay. So, then R is equal to, okay. So, R is equal to partial derivative of ZU with respect to x. So, ZUU into x minus ZUB into x plus ZU minus, now let us put the value of partial derivative of ZB with respect to x here. So, ZUB into x minus ZBB into x plus ZB, and what we get ZUU into x square minus ZUB into x square plus ZU, and what we get here this x gets multiplied to this and we get minus ZUB into x square and we get plus ZBB into x square and we get minus ZB. Okay, so what we get ZUU x square minus 2ZUB x square plus ZBB x square plus ZU minus ZB. Okay. So, we have found the value of R. Now, let us find the value of T. So, for T is this. Okay. So, first we find Q. Okay. Q is equal to this is delta Q by delta Y. So, first we find this. So, this is ZU into UY plus ZB into BY. Now, UY is equal to how much? UY is equal to 1. Okay. From this relation BY is also 1. So, we get here ZU plus ZB. Okay. Now, T is equal to delta over delta Y of ZU plus delta over delta Y of ZB. Okay. So, we have the value of delta Z by delta Y for any function Z of U and B. So, replacing Z by ZU there we have, okay. So, ZUU plus Z when you replace by ZU. So, we get ZUB, and when we do this for ZB function, ZB is also a function of U and B. So, replacing Z by ZB we get ZUB plus ZBB. So, this imply that T is equal to we add these two values, this and this. Okay. So, we get ZUU plus 2 ZUB plus ZBB. Okay. We have got the values of R and T, and what is x here? If you see x square, if subtracting u and subtracting v from u, okay, we get u minus b. You can see u is by plus x square by 2, b is by minus x square by 2. So, u minus b is equal to x square. Okay. So, let us put the value here. R is equal to this is R. Okay. This is R, and when I multiply T by x square, okay, and subtract, what we get? R minus x square into T. How much is that? From this we subtract x square times T. So, x square into ZUU will cancel, and then x square into ZBB, that will also cancel. Okay. And here x square, when you multiply and subtract, minus 2x square ZUB, okay, will add to this. Okay. So, we will get minus 4 ZUB into x square plus ZU minus ZB equal to 0. Okay. So, or we can say I take this term to the other side. So, 4 ZUB into x square is equal to ZU minus ZB. Okay. Or I can say ZUB equal to 1 by 4 x square into ZU minus ZB. Okay. X square, as I have already said, x square is u minus b. So, we get 1 over 4 u minus b into ZU minus ZB. Okay. So, this is how we get ZUB equal to 1 by 4 into u minus b ZU minus ZB. So, this is the required canonical form. With this I would like to conclude my lecture. Thank you very much for your attention.